Ground-based telescopes have given us an enhanced perspective on the stars, more light than can be seen with our eyes. Numerous instruments have existed throughout history and were designed to study space, but the scientific method has been the closest thing to a true leap until the James Webb Space Telescope. Literally, the telescope was intended for use in traveling back to the universe's beginning, and that is precisely what it has accomplished. In terms of exoplanets, we now have the official representation of the City of Lights. A significant historical event, Proxima b, changes everything. 18 more distinct images are anticipated to be accumulated, one copy for each mirror. But that's not all. The James Webb Telescope recently produced the most precise image of another exoplanet. Join us in investigating this remarkable discovery and what the James Webb Space Telescope could imply for our future. If you're interested in learning more about the universe and its vast regions, consider subscribing to our channel. Be sure to like this video and activate the notification bell. With gratitude to James Webb, researchers can now examine the past, back in time to when the universe was less than 200 million years old. The information gleaned from this invention will most likely enable us to travel back in time and learn more about the universe's evolution. This is not everything. The telescope is also able to take photographs of some of the initial galaxies that formed, allowing us to observe the first stars in the universe, shining in the pitch-black void of space. But how does the JWST achieve its incredible capabilities? Well, with a massive 21-foot diameter mirror, it collects and reflects light toward the spacecraft's instruments. Speaking of instruments, each of the 4 on board, James Webb is designed to capture different kinds of light and provide a unique perspective on the universe. The near-infrared camera, NIRCam, is the primary camera, used to take stunning pictures of faraway nebulas, galaxies, and other cosmic wonders. The near-infrared spectrograph, NIRSpec, analyzes light into its constituent parts to gather more information about observed objects. The mid-infrared instrument, MIRI, captures light in the mid-infrared range, studying exoplanets, our own solar system, and the early universe. Finally, there's a fine guidance sensor used for precise pointing, which also has spectrographic capabilities for infrared light. At this point, you might wonder, why did NASA choose infrared for the James Webb Telescope? There are numerous types of light available, but the infrared option was chosen for several reasons. First, infrared light can penetrate gas and cosmic dust that would otherwise block visible light. In addition, studying cool objects, such as stars, exoplanets, and distant galaxies, is ideal in infrared. JWST's infrared capabilities allow us to detect features that would be invisible using other types of light. The JWST broke new ground by capturing its first clear image of an exoplanet. The exoplanet's name is HIP 65426b, discovered in 2017. It is located 100 times farther from its host star than Earth is from the Sun. To examine this enormous gas giant, researchers used the James Webb Telescope with a variety of filters. The result, a combined image of the exoplanet, marks a thrilling accomplishment for astronomers. Sasha Hinckley, a scientist at the University of Exeter in the UK and lead on these observations, said this moment is not only beneficial for the Webb telescope but for astronomy as a whole. The size of this exoplanet makes it unique, approximately 12 times the size of Jupiter, and its vast distance from its host star makes it easier to capture a direct image using Webb. However, direct imaging of exoplanets isn't just about stunning pictures. It's about understanding how planets form and what conditions they have, possibly even finding planets capable of supporting life, a goal pursued for decades. While current research suggests that finding a habitable planet is still uncertain, the James Webb Telescope has the power to zoom in on planets like never before. If a habitable exoplanet exists, JWST may be the first to detect it. What happened next exceeded all expectations. Scientists revealed that the James Webb Telescope had successfully observed some of the oldest galaxies humans have ever seen, formed, when the universe was just 2% of its current age. These 4 galaxies are the most distant ever observed, located 13.4 billion light-years away. Let's take a moment to consider that. The light from these galaxies took 13.4 billion years to reach our telescopes. Despite that unimaginable distance, JWST was able to detect them and take their pictures, capturing how they looked over 13 billion years ago. Identifying these ancient galaxies was no easy task. First, scientists had to locate them, a challenge due to their immense distance. But thanks to JWST's infrared capabilities, it could detect even the faintest signals. Researchers then named the 4 galaxies. However, identifying the galaxies was only the beginning. To verify their age, scientists used JWST's near-infrared spectrograph to measure the redshift, the stretching of light wavelengths as the universe expands. A redshift of 13.2, the highest ever recorded, confirmed the galaxy's extreme age. This discovery is hard to overstate. These galaxies formed before our own galaxy, or even the first stars in the Milky Way. Webb's photographs give us a glimpse into the very earliest days of the universe. This kind of discovery reshapes our understanding of the cosmos and challenges long-held theories. Recently, researchers have even begun exploring whether Webb could capture city lights on distant exoplanets, a dreamlike idea that speaks to the telescope's sharpness and sensitivity. Despite this, human activity on Earth may appear to be a difficult challenge. The circumstances, however, are favorable for doing so. Take, for instance, the star closest to the Sun, the red dwarf Proxima Centauri. It can be found at a distance of 4.25 light-years, where a planet, enjoyed by astronomers, Proxima b, is located in the habitable zone around its star. It is thought that Proxima b has a tidally locked configuration, with one side continuously lit by day and the other side in perpetual darkness. If Proxima b harbors a technological civilization, it's possible that they have covered the day side of the planet with solar panels to produce electricity and supply illumination that would also heat the night side. This is where the James Webb Space Telescope comes into play. Recently published research papers have shown that the James Webb Telescope could potentially pick up artificial city lights on the permanently dark side of Proxima b. Despite the fact that such lighting is dim compared to Earth's nighttime surroundings, the telescope may still detect it, though it is limited to a frequency band 1,000 times narrower than starlight. Future space telescopes that NASA envisions, such as those using optical, infrared, and ultraviolet capabilities, will be even more sensitive to weaker levels of artificial light present on Proxima b. The idea that there could be a planet with artificial lights more than 4 light-years away is astounding. It's a reminder that there is still so much to discover. By observing the universe through telescopes, we are one step closer, like James Bond, to understanding everything that occurs both within our solar system and in distant galaxies. With that, our video for today concludes. We'd love to know what you think in the comments. Do you believe the James Webb Telescope is the solution to all our scientific questions, or do we need even more advanced telescopes? Please give the video a thumbs up, and we'll see you in the next one. The James Webb Space Telescope continues to redefine the scope of modern astronomical possibilities. As researchers sort through the vast data it collects, new insights emerge daily, reshaping our understanding of space and its ability to detect faint light from the earliest moments of the universe. This gives researchers a kind of time machine, allowing them to investigate conditions shortly after the Big Bang. This capability has profound implications for cosmology, presenting evidence that challenges long-held beliefs and introduces new theories about the formation and structure of the universe. More than just identifying galaxies and exoplanets, the James Webb Telescope enables scientists to determine the chemical makeup of distant worlds. By observing light that passes through a planet's atmosphere during transit events, researchers can identify molecules such as methane and carbon dioxide, even potential biosignatures. These insights are crucial for evaluating a planet's ability to support life. Webb's precision, which surpasses that of its predecessors, allows these compounds to be detected even in relatively calm environments on small exoplanets that bring us closer to finding a second Earth. One remarkable achievement of the telescope is its contribution to understanding the life cycle of stars. It can study the dense, opaque birthplaces of stars, clouds of gas and dust, by observing in the infrared spectrum, which penetrates these regions. These observations have revealed complex structures, including how disks of matter transform into solar systems. Webb also monitors dying stars, supernova remnants, and black holes, helping scientists understand the intricate processes of stellar death and the recycling of matter into future generations of stars and planets. Its role in studying our own solar system has been equally impactful. It has provided high-resolution images and spectral information about objects such as Jupiter, Saturn, and their moons, including intriguing candidates like Europa and Enceladus, which may harbor subsurface oceans. Observations of distant objects in the Kuiper Belt and Oort cloud offer insights into the early history of the solar system and its dynamic evolution. The telescope's global reach, thanks to the collaboration between NASA, the Canadian Space Agency, and the European Space Agency, exemplifies international scientific cooperation. The data from Webb is shared widely, allowing researchers around the world to contribute to breakthrough discoveries. This transparency accelerates progress and ensures that the benefits of science are shared globally. As technological advancements continue, there's growing momentum behind missions that might complement Webb's findings. These future telescopes may operate in different electromagnetic ranges or be specially designed to detect biosignatures. Some may even be placed in unique orbits or stationed on the Moon, where minimal seismic activity and no atmosphere offer ideal observing conditions. The James Webb Space Telescope remains unparalleled in its ability to peer deep into the universe and far into the future. Its observations have already caused paradigm shifts in astrophysics and planetary science. We are only at the beginning of what is expected to be a long and fruitful mission. The next wave of discoveries doesn't depend solely on whether we build more telescopes. What matters is how each step brings humanity closer to answering profound questions about our origins, our place in the cosmos, and whether we are alone in the vast expanse of existence.